On November 5th, 2018, at a distance of 119 astronomical units from the Sun, Voyager 2's plasma detector recorded something that took scientists nearly a full year to fully understand. No other functioning instrument anywhere in either Voyager spacecraft has ever measured this boundary directly. No pre-2019 model predicted the number that came back. It is not a quiet, empty edge of the solar system. It is a wall of plasma hot enough to sound like something out of science fiction. Stay with me, because what NASA found when it went back through that data is still shaping how scientists think about the only shield our planet has ever had. I cover real space missions here every week. No fiction, just the data. Subscribing costs nothing and helps more than you'd think. Let us go back to the beginning. To understand why this finding mattered, you first need to understand what Voyager 2 was actually flying through, and why nobody was entirely sure what it would find. The Sun does not just sit quietly in the middle of the solar system. It constantly exhales a stream of charged particles called the solar wind, blasting outward in every direction at speeds that would vaporize almost anything built on Earth. That outward pressure inflates an enormous bubble around the entire solar system, a bubble called the heliosphere, stretching far past the orbit of Pluto. Somewhere out past that bubble, the outward push of the solar wind runs out of strength, and the faint pressure of the interstellar medium, the thin plasma and radiation drifting between the stars, takes over instead. Scientists gave the boundary between those two regions a name decades before anyone could actually reach it: the heliopause. This wasn't a guess pulled out of thin air. It was built from real physics and real measurements of the solar wind's pressure dropping off with distance, and it made a specific, testable prediction that crossing the heliopause should look like passing from one regime of space into a completely different one, with different density, different temperature, and a different magnetic character on each side. Both Voyager spacecraft were originally built for a much smaller job than any of this. Launched in 1977, they were designed to fly past Jupiter and Saturn on a mission expected to last about 4 years, using the electronics standard of an era before the personal computer even existed. Voyager 2 went on to do something no other spacecraft in history has managed before or since, using a rare alignment of the outer planets to fly past Jupiter, Saturn, Uranus, and Neptune in a single continuous, grand tour, becoming the only spacecraft ever to visit all 4 gas giants. That planetary tour officially ended in 1989 after the Neptune flyby, and by any reasonable standard of the original mission plan, Voyager 2's job was finished. Everything since then, the interstellar crossing, the plasma readings, the temperature anomaly, is bonus science nobody in 1977 explicitly promised. That's an important detail, because it means the instruments now confirming a temperature nobody predicted were never built with this specific measurement in mind. They were repurposed, decades later, for a mission their original engineers never fully anticipated. Voyager 1 technically crossed that boundary first on August 25, 2012, becoming the first human-made object to leave the heliosphere. But there was a catch that made Voyager 1's crossing scientifically incomplete. Its dedicated plasma science instrument, like the one built specifically to measure the temperature, density, and speed of the plasma around it, had stopped working decades earlier, shortly after its 1980 flyby of Saturn. Voyager 1 could tell scientists that something had changed. Cosmic ray levels spiked, solar particles vanished, but it couldn't tell them exactly what the plasma itself was doing at the moment of crossing. That instrument, called the Plasma Science Experiment, was still very much alive on Voyager 1's twin. And on November 5th, 2018, at 119 astronomical units from the Sun, Voyager 2 crossed its own heliopause, roughly 2 astronomical units, closer to home than where Voyager 1 had crossed 6 years earlier. A small but telling difference, since the heliosphere itself isn't a fixed sphere, but something that swells and contracts with the Sun's own activity, like a lung breathing in and out. For the first time, scientists finally had a fully functioning plasma detector riding straight through the boundary they had spent decades theorizing about. What it sent back took the better part of a year to properly analyze, and the results, published in Nature Astronomy in November 2019 by a team led by MIT's John Richardson, were not what anyone had modeled. Here is the number that mattered. Models built before Voyager 2's crossing predicted the interstellar plasma just beyond the heliopause should sit somewhere between 15,000 and 30,000 Kelvin, already scorching by any everyday standard, but within a range scientists felt reasonably confident about. What Voyager 2's plasma instrument actually recorded, once researchers finished combing through the data, was a temperature between 30,000 and 50,000 Kelvin. Read that again. That upper figure, 50,000 Kelvin, works out to roughly 90,000 degrees Fahrenheit, hotter than the surface of most stars, sitting in a region of space most people picture as an empty, freezing void. This is where the phrase that later spread across headlines and news segments came from: a wall of fire at the edge of the solar system. Here's the part that makes it stranger rather than more dangerous, though, and it's the detail that gets left out of almost every dramatic headline. This isn't heat, in the way you'd feel heat from a stove or a flame. Temperature, in a plasma this thin, is really just a measurement of how fast individual particles are moving, and in the boundary region Voyager 2 crossed, there are so few particles per cubic centimeter that there simply isn't enough mass to transfer that motion into anything a human body, or even a spacecraft's exterior, would ever register as warmth. Voyager 2 flew straight through a wall of fire hot enough to be called a wall of fire, and it never even needed a thermal shield to survive it. Think about what that actually means for a second. Put a single grain of sand in an empty football stadium, and you have roughly the kind of particle density we're talking about, except each grain is moving fast enough to register a temperature that would vaporize a human being if it were sitting in your kitchen instead of 10 billion miles from anyone's kitchen. It is not a contradiction. It's a reminder that two of the most basic words in physics, hot and dangerous, don't always mean the same thing once you leave the atmosphere that taught us to link them. But the temperature wasn't the only thing that didn't match the old models. As Voyager 2 approached the heliopause, its instruments picked up something researchers hadn't expected to see so clearly: a boundary region roughly 1.5 astronomical units wide, about 140 million miles, where the surrounding plasma noticeably slowed down, heated up, and became roughly twice as dense as the typical plasma inside the outer heliosphere. Sit with that for a second. That's a region wider than the distance from the Sun to Earth, acting as a kind of pressurized antechamber before the true boundary, something no spacecraft had ever mapped in this kind of detail before. Then, just inside that outer region, Voyager 2 hit a second, much thinner layer, only about 0.06 astronomical units wide, roughly 9 million miles, where the density and magnetic field jumped again, sharper and faster. And then the actual crossing itself, the true heliopause, happened in under a single day. Not years of gradual transition, not even weeks. Less than 24 hours, and Voyager 2 went from one physical regime of the universe into an entirely different one. What most people are not seeing when this story gets told is that the boundary isn't the clean, single line every diagram in a textbook draws it as. It's layered, structured, and considerably more violent, in a physics sense, than the old models ever suggested. A nested set of transition zones, rather than a single wall. Here is where this stops being abstract. The heliosphere that Voyager 2 spent 41 years crossing isn't just an interesting shape in a diagram. It is the only reason Earth has been livable for the entire span of human history. That bubble of solar wind acts as a shield, deflecting a huge share of the high-energy galactic cosmic radiation that would otherwise bombard every planet in the solar system unfiltered. Understanding exactly how that shield behaves at its outer edge, how sharp its walls really are, how hot and turbulent the boundary region actually gets, whether it flexes and thins during periods of low solar activity, is not a purely academic question. It is a direct input into every serious model of how much cosmic radiation reaches the inner solar system today, and how that exposure might change as the Sun's own 11-year activity cycle rises and falls. The wall of fire Voyager 2 flew through in 2018 sits at the outer skin of the only thing standing between Earth and the raw radiation environment of the rest of the galaxy. That's not science fiction. That's the boundary of home. Getting that data back to Earth at all, though, nearly didn't happen. And the crisis that almost ended it came not from the plasma itself, but from something far more mundane. A single sequence of commands sent from a control room in California. On July 21st, 2023, engineers at NASA's Jet Propulsion Laboratory transmitted a routine set of scheduled commands to Voyager 2, part of the normal planned maintenance every deep space mission requires. Buried in that sequence was a mistake nobody caught until it was too late. A set of instructions that, when executed on board, tilted Voyager 2's 12-foot dish antenna just 2 degrees away from Earth. 2 degrees. That's it. Not a dramatic swing, not a violent malfunction, just 2 degrees out of a full 360 on an antenna more than 12 billion miles from home. And 2 degrees was enough to sever the link entirely. Voyager 2 went silent. Not destroyed, not malfunctioning internally, simply no longer pointed in a direction where anyone on Earth could hear it, or send it anything at all. Here's where it gets worse. The mission team knew in principle how to fix this. Voyager 2 was programmed to perform an automatic realignment maneuver periodically, resetting its orientation using its onboard sun sensor to make sure its antenna kept pointing home. But that maneuver wasn't scheduled to happen again until October 15th, nearly 3 months away. 3 months of near total silence from a 46-year-old spacecraft, at a distance where a single one-way radio signal already takes over 18 hours to arrive, was an agonizing prospect on its own. But it was worse than just an inconvenient wait. A spacecraft that old, with decades of accumulated wear on every mechanical part, going completely unmonitored for 3 months carried real risk. If anything else went wrong in that window with no way to command a correction, the mission itself could have been lost entirely, permanently, with no one on Earth ever finding out why. The team decided waiting for October wasn't good enough. They needed to try something faster, and there was no guarantee it would work. Every option on the table came with its own risk. Do nothing and wait for the automatic realignment, and you accept 3 months of a 50-year-old spacecraft flying blind. Osher with engineers on Earth, unable to intervene if a single system failed in the meantime. Attempt an early fix, and you risk sending a command that either does nothing at all because the signal is too faint to be received cleanly, or worse, gets partially received and corrupted, potentially locking the antenna into an even more difficult position to correct. There was no safe option. There was only the option that felt less terrible than the alternative. On August 1st, engineers using multiple dishes of the Deep Space Network detected something. A faint carrier signal, a kind of electronic heartbeat, confirming Voyager 2 was still alive and functioning, even if its antenna was still pointed the wrong way. That was hope, but not contact. The signal was far too weak to carry any actual data. So on August 4th, the team at the Deep Space Network's Canberra, Australia facility attempted something dramatic. They used the most powerful transmitter in the entire network to send what NASA itself later described as an interstellar shout. A command blasted out at roughly 400 kilowatts, instructing Voyager 2 to physically reorient its antenna back toward Earth. There was no way to know in advance whether it would work. The signal had to travel more than 12.3 billion miles, arrive precisely enough to be received by a probe that could no longer hear normal transmissions clearly, and then be correctly executed by a computer running code written in the 1970s. It took 37 hours, round trip, before anyone on Earth would know the outcome, one way or the other. At 12:29 a.m. Eastern Time, the response came back. Voyager 2 had heard the shout. Its antenna had turned. Science and telemetry data began flowing again, and the wall of fire findings that would reshape scientists' understanding of the heliopause kept coming uninterrupted from that point forward. Here is what is happening right now in 2026. Both Voyager spacecraft are closing in on their 50th anniversary in orbit, and both are running critically low on the one resource no engineer on Earth can refill, electrical power. Each spacecraft's 3 radioisotope thermoelectric generators, converting the heat of decaying plutonium-238 into usable electricity, are losing roughly 4 watts every single year, a slow and completely irreversible bleed that has already cut Voyager 2's original output nearly in half. Voyager 2 is currently about 21.35 billion kilometers, roughly 13 billion miles, from Earth, and after the shutdown of its low-energy charged particles instrument in March 2020, it has 3 functioning science instruments left: the cosmic ray subsystem, the magnetometer, and the plasma wave subsystem. The very lineage of instrument that caught the wall of fire in the first place. Just weeks ago, engineers successfully completed a coordinated power-saving maneuver the team has nicknamed the Big Bang, a single, carefully sequenced swap of several onboard systems for lower power alternatives, executed all at once rather than gradually, precisely because Voyager 2's power margin had grown too thin for anything less drastic. According to the mission team, the successful maneuver is expected to buy Voyager 2's 3 remaining instruments roughly another year, possibly 2, of continued operation, a reprieve the spacecraft badly needed. Engineers are now preparing to attempt the same maneuver on Voyager 1, which is farther from Earth and has even less power margin to work with. None of this is guesswork or optimistic projection. It's the same kind of careful, incremental engineering that kept the mission alive through the antenna crisis in 2023, applied now to a slower, quieter emergency. A power budget that simply cannot be replenished, only rationed more cleverly than it was the year before. Every watt saved by turning off a heater or swapping a component buys the mission not years, usually, but months. And those months are precisely what stand between a working plasma wave subsystem and a fully silent spacecraft. And there's a specific date locked in ahead, one that requires no prediction and no modeling, only geometry and the constant, unchangeable speed of light. Voyager 2 launched from Cape Canaveral on August 20th, 1977, 16 days before Voyager 1, despite carrying the higher spacecraft number because Voyager 1 took a faster trajectory and overtook its twin shortly after launch. That means Voyager 2's 50th anniversary in space arrives on August 20th, 2027, just over a year from now, an exact date already fixed on the calendar. That the mission team is now actively working to ensure the spacecraft survives to see with at least one instrument still transmitting. Nothing about that date is speculative. It is simply how long ago the spacecraft left Earth, counted forward to the day. What is genuinely uncertain is what state Voyager 2 will be in when that day arrives, whether it will still be listening to the interstellar plasma with a working detector, Or whether by then engineers will be counting down the last watts of a 50-year-old machine with nothing left to give. Now for the part that doesn't resolve as neatly as headlines about a wall of fire tend to suggest. Scientists still do not have a single, fully agreed upon explanation for exactly why the plasma in that boundary region runs as hot as it does. One leading explanation points to a process called magnetic reconnection, where tangled magnetic field lines in the boundary region snap and reconnect, releasing enormous amounts of stored magnetic energy directly into the surrounding particles and accelerating them to the speeds that register as extreme temperature. A competing explanation focuses on simple compression, as the outward pushing solar wind runs into the resistance of the interstellar medium. The plasma gets physically squeezed into a smaller volume in that boundary layer, and compressing any gas naturally raises its temperature. No exotic mechanism required. Researchers studying the Voyager 2 data have been careful not to declare the debate settled, and subsequent papers examining Voyager 1's own less complete measurements of a similar boundary region have found their own inconsistencies with the clean layered boundary picture, including open questions about whether a stagnation region reported near Voyager 1 even exists in the way earlier papers suggested. What most people are not seeing when the wall of fire gets reduced to a single dramatic headline is that the actual heliophysics community treats this as an open, actively contested question, not a closed case. Both explanations, magnetic reconnection and simple compression, could turn out to be partially right, working together rather than competing, and resolving that question fully will likely require the next generation of dedicated heliophysics missions, not another pass through data these two aging spacecraft have already sent home. Zoom out from the plasma numbers for a moment, and there's a bigger pattern worth noticing. Voyager 2 was never designed to answer a question this specific about the structure of interstellar space. It was built in the 1970s to fly past Jupiter, Saturn, Uranus, and Neptune, a mission that formally ended in 1989. Everything it has done since then, including flying through a boundary hot, enough to earn the nickname Wall of Fire, is bonus data from a machine that simply refused to stop working on schedule. That's not a coincidence, and it's not luck in the way people usually mean it. It's the direct result of a small number of engineers spread across 5 decades, choosing again and again to keep listening to a signal. Most institutions would have long since written off as not worth the cost. Real scientific progress, at the edge of what humanity can reach, rarely looks like a single triumphant announcement. It looks like an old machine, built by people who are now retired or gone, still returning data to a team that has to relearn, generation after generation, how to listen to it properly. The heliopause itself is not a wall meant to keep anything out. It is simply where 2 different pressures happen to balance, for now shaped by a sun that is itself slowly changing. Even that balance is not permanent. As the sun's activity rises and falls across its own long cycles, the entire boundary breathes in and out over centuries, meaning the edge of the solar system. Voyager 2, measured in 2018, is not a fixed line on a map. It is a moving negotiation between our star and the galaxy it sits inside, and we have, for the first time in human history, an actual set of numbers describing exactly how that negotiation looks from the inside. Think about what that means for how we should treat the next 50 years of exploration, not just the last 50. Every future mission gets designed against a specific projected lifespan, reviewed and budgeted around numbers that assume the hardware will do exactly what it's asked and nothing more. Voyager 2 is the permanent counterexample to that assumption. Proof that some of the most consequential data a spacecraft will ever return might not arrive until decades after its official mission ended, collected by instruments nobody built with that specific discovery in mind. The scientists who finally confirmed the Wall of Fire's true temperature in 2019 were, in many cases, not even working in the field when Voyager 2 launched in 1977. That's not an incidental detail. That is the actual mechanism by which this kind of long-horizon science happens. One generation builds the instrument, and a much later generation finally has the tools, the patience, and the reason to listen to what it's been saying the whole time. There is a record still bolted to Voyager 2's frame, a gold-plated copper disc containing greetings in 55 languages, birdsong, whale calls, and a map showing the way back to a small, undistinguished star near the edge of an ordinary galaxy. It was sealed in 1977 by a team that included Carl Sagan, who once described the record as a message cast into the cosmic ocean, without much hope that it would ever be found, but with the quiet conviction that it said something true about the civilization that sent it. That bottle has now passed through a wall of plasma hot enough to be called fire, cold enough in actual substance to leave not a single mark on its casing, and kept moving. It carries no memory of the antenna that nearly stopped listening, no record of the year scientists spent puzzling over its own temperature readings. It simply continues outward, at 34,000 miles an hour into a darkness that, according to the very instrument riding along with it, is not silent at all. It burns without heat and refuses to behave the way anyone expected it to. So here's everything. In one breath, Voyager 2 crossed the heliopause on November 5th, 2018, becoming the first spacecraft with a working plasma instrument to measure that boundary directly, and the year-long reanalysis of that data, published in Nature Astronomy in 2019, revealed a layered, structured region far more violent than old models predicted. Plasma reaching 30,000 to 50,000 Kelvin, a wall of fire that poses no real danger only because the particles are too sparse to transfer heat. In 2023, a routine command error nearly ended the mission's ability to report any of it, severing contact for 2 weeks until an interstellar shout from Australia's Deep Space Network brought the antenna back around. If you want to know whether Voyager 2 makes it to that 50th anniversary with a working instrument still listening, or whether the Big Bang maneuver planned next for Voyager 1 succeeds or fails, subscribe and turn on notifications, because I'll be covering it the moment NASA confirms either outcome. Here's my question for you. Given everything you just heard, would you rather NASA spend its remaining budget keeping these two 50-year-old machines alive a few more years, or redirect that money toward building a dedicated new probe to follow them out? Tell me which one in the comments. I read every single one.